up, Blockchain Nation? What up, YouTube? Thank you for taking the time to watch this video. And if you haven't subscribed, please hit the subscribe button below so that you can get weekly notifications whenever I release one of these videos. And for those who watch consistently, I want to say a big thank you. You're far too kind. So how does Bitcoin work? Personally, I do not believe in reinventing the wheel. I was thinking of coming up with some graphs and diagrams and stuff of how to explain this, but I've actually I want to recommend a resource that I've actually watched a couple of times. It's by 3 Blue Brown. As you can see, it has over 3 million views. It was in 2017. This is one of the best explanations of how Bitcoin works, in my personal opinion. It's really great, but I've shown this to some people and they have had some issues understanding this. If you watch this video already and you understand it already, then you don't have to watch my video. So if you can watch through this, if you can look through this and get the whole concept, then I'll recommend you just watch it. But for some people, they just need some kind of clarification on what this video explains, so that's what I'm trying to do. So it really is a good resource, and I'll put a link below so you can watch it yourself. So I'm just going to walk through some aspects of this video, not the entire thing. As you can see, it's almost half an hour long, just some key features, and you can watch the rest of the video to get more information. So if you're ready, say I'm ready. All right. So basically, it's going to be in 6 parts. The first part, we're going to talk about ledgers, highlighting how this, 6 parts. I'm breaking this video into 6 different parts. There's a lot to it, but I'm just highlighting these features. And I think, in my opinion, if you understand these concepts, it will really help to understand the rest of the video and, as a whole, how Bitcoin and proof of work works. So, I like that, how proof of work works. Anyways, so the first part talks about ledgers. Second part about digital signatures. Third part about the important attributes of Bitcoin, or an important attribute of Bitcoin. And then the last 3 parts, it really goes into details of proof of work, which is what I'm going to try to do. So if you're ready, say I'm ready. So let's just watch the first part that talks about ledgers. I'll just play a little bit and then I'll explain. Okie dokie.
But to start, I want you to actually set aside the thought of cryptocurrencies and all that just for a few minutes. We're going to begin the story with something more down to earth: ledgers and digital signatures. If you and your friends exchange money pretty frequently, paying your share of the dinner bill and such, it can be inconvenient to exchange cash all the time. So you might keep a communal ledger that records all of the payments that you intend to make some point in the future. Alice pays Bob $20, Bob pays Charlie $40, things like that. This ledger is going to be something public and accessible to everyone, like a website where anyone can go and just add new lines. And let's say that at the end of every month, you all get together, look at the list of transactions, and settle up. If you spent more than you received, you put that money in the pot, and if you received more than you spent, you take that money out. So the protocol for being part of this very simple system might look like this. Anyone can add lines to the ledger, and at the end of every month, you all get together and settle up. Now, one problem with a public ledger like this is that anyone can add a line. So what's to prevent Bob from going and writing Alice pays Bob $100 without Alice approving? How are we supposed to trust that all of these transactions are what the sender meant them to be?
So that's the first piece of it. So I think this kind of explains itself. So what Bitcoin is, or what a blockchain is. But let me just use what the Bitcoin network is. It's just a ledger of transactions. Pretty much that's what it is. So like a basic ledger, like how this example explains, if all these people are they go out to eat and they have a way of settling accounts, or they have like basically a way of keeping records of transactions that occur between members of the group, then they have a ledger, a public ledger for doing that. So at its core level, that's what Bitcoin is. It's a distributed ledger, but we'll get into all that. But I think this kind of explains itself. So I'll just move on and then we'll just listen to the rest of it.
Well, this is where the first bit of cryptography comes in: digital signatures. Like handwritten signatures, the idea here is that Alice should be able to add something next to that transaction that proves that she has seen it and that she's approved of it. And it should be infeasible for anyone else to forge that signature. At first, it might seem like a digital signature shouldn't even be possible. I mean, whatever data makes up that signature can just be read and copied by a computer, so how do you prevent forgeries? Well, the way this works is that everyone generates what's called a public key private key pair, each of which looks like some string of bits. The private key is sometimes also called a secret key, so that we can abbreviate it as SK while abbreviating the public key as PK. Now, as the name suggests, this secret key, it's something you want to keep to yourself. In the real world, your handwritten signature looks the same no matter what document you're signing. But a digital signature is actually much stronger, because it changes for different messages. It looks like some string of ones and zeros, commonly something like 256 bits, and altering the message even slightly completely changes what the signature on that message should look like. Speaking a little more formally, producing a signature involves a function that depends both on the message itself and on your private key. The private key ensures that only you can produce that signature, and the fact that it depends on the message means that no one can just copy one of your signatures and then forge it on another message. Hand in hand with this is a second function used to verify that a signature is valid. And this is where the public key comes into play. All it does is output true or false to indicate if this was a signature produced by the private key associated with the public key that you're using for verification.
Awesome. So this is the second piece, which talks about digital signatures. So like the example from the beginning of that public ledger, just to be able to validate or confirm that a transaction actually occurred, you want to be sure that a transaction has a signature of the person who made the transaction. So a transaction in this case is what we call like a message. A transaction can be a message. So like Alice pays Bob, Bob pays Charlie. So Alice paying Bob is one message or one transaction, and Bob paying Alice is another message and a transaction. So how do we know that Alice really did pay Bob and it wasn't something forged or made up? So that's what the concept comes in of digital signatures. So at the score level, so a signature basically is generated using this sign function, where it takes a message or like a transaction, Alice paying Bob, and SK means a private key. So unlike traditional systems whereby you have a debit card or a credit card, don't try and use this because there's nothing on it. Here it just doesn't make sense. Imagine keeping all your credit card information on a file whereby, or like on Amazon or all these shopping sites that we all go to, and this information is available for anyone to steal, forge, and how we have people's credit card information always getting compromised. But the great thing about the private key, public key concept is that I can show anybody my public key, which is great, but my private key is something that's private to me. So it's more, it's safer than having all these interesting cards, which are going to be junk probably by the time you're watching this in the next 5-10 years, who knows. Anyways, the great thing about this is that it uses this sign function. It takes a message and a private key to give you a signature. So that's how a signature is generated. And then you can also verify that this signature came from whoever it originated from by taking that message and also using its public key. This is private key. Public key to verify that this signature actually came from who the signature was supposed to come from. So which is cool. So I hope that explains it. So the third part will be importance of Bitcoin. So let me just go there.
This is the first important thing to understand about Bitcoin, or any other cryptocurrency. What it is a ledger. The history of transactions is the currency. Of course, with Bitcoin, money doesn't enter the ledger with people buying in using cash. I'll get to how new money enters the ledger in just a few minutes. But before that, there's actually an even more significant difference between our current system of ledger dollars and how cryptocurrencies work. So far, I've said that this ledger is in some public place, like a website where anyone can add new lines. But that would require trusting a central location, namely, who hosts the website, who controls the rules of adding new lines. To remove that bit of trust, we'll have everybody keep their own copy of the ledger. Then when you want to make a transaction, like Alice pays Bob 100 ledger dollars, what you do is broadcast that out into the world for people to hear and to record on their own private ledgers. But unless you do something more, this system is absurdly bad. How could you get everyone to agree on what the right ledger is? When Bob receives a transaction, like Alice pays Bob 10 ledger dollars, how can he be sure that everyone else received and believes that same transaction? That he'll be able to later on go to Charlie and use those same 10 ledger dollars to make a transaction? Really, imagine yourself just listening to transactions being broadcast. How can you be sure that everyone else is recording the same transactions and in the same order? This is really the heart of the issue. This is an interesting puzzle. Can you come up with a protocol for how to accept or reject transactions and in what order, so that you can feel confident that anyone else in the world who's following that same protocol has a personal ledger that looks the same as yours? This is the problem addressed in the original Bitcoin paper.
So this is great. So this is really the wonderful thing about Bitcoin. So the ledger that hosts all these transactions or messages is distributed, which means that everybody has a copy, and that's very challenging. Imagine it's one thing to have a notebook where I record all these transactions, which will be my ledger, but it's one other thing to when you have so millions and thousands or so many transactions that everybody is actually recording every single transactions. That's the beautiful thing about Bitcoin and blockchain technology. It's able to allow you to have a ledger that's distributed. So traditional systems, you have all those transactions or that ledger in one place where all the messages or all the transactions are going to that central repository. So I can always just go to that single source of truth and know that, hey, this particular repository or this particular single ledger has all that information. But the great thing about Bitcoin and blockchain technology is that it's able to solve the problem whereby even though so many people have a copy of the ledger, it's still in sync and everybody comes to consensus or agreement that we all have the same transactions on our ledger, and our ledger will always should be up to date at every point in time or every 10 minutes. So that's a wonderful thing about attributable Bitcoin. So now let's go into the meat and potatoes of this. How does it happen? Well, this is where proof of work comes in.
The solution that Bitcoin offers is to trust whichever ledger has the most computational work put into it. I'll take a moment to explain exactly what that means. It involves this thing called a cryptographic hash function. The general idea that we'll build to is that if you use computational work as a basis for what to trust, you can make it so that fraudulent transactions and conflicting ledgers would require an infeasible amount of computation to bring about. Again, I'll remind you that this is getting well into the weeds beyond what anyone would need to know just to use a currency like this. But it's a really cool idea, and if you understand it, you understand the heart of Bitcoin and of other cryptocurrencies. So first things first, what's a hash function? The inputs for one of these functions can be any kind of message or file, it really doesn't matter. And the output is a string of bits with some kind of fixed length, like 256 bits. This output is called the hash or the digest of the message, and the intent is that it looks random. It's not random, it always gives the same output for a given input. But the idea is that if you slightly change the input, maybe editing just one of the characters, the resulting hash changes completely. In fact, for the hash function that I'm showing here, called SHA-256, the way the output changes as you slightly change that input is entirely unpredictable. You see, this is not just any hash function. It's a cryptographic hash function. That means it's infeasible to compute in the reverse direction. If I show you some string of ones and zeros and ask you to find an input so that the SHA-256 hash of that input gives this exact string of bits, you will have no better method than to just guess and check. And again, if you want a feel for how much computation would be needed to go through 2 to the 256 guesses, just take a look at the supplement video. I actually had way too much fun writing that thing.
Yeah, so just to explain this, so imagine you have a string in this field. So SHA-256 is an encryption algorithm, so to speak. So imagine you do a SHA-256, it's a hashing function, excuse me. So if you do a SHA-256 on a string here, and let's say this string has the word philosophy, the desired output will differ if the words philosophy were changed, like if it was a capital, where did he do that? So that way, yeah, here we go. So these are the words 3 blue brown. So running a SHA-256 on 3 blue brown will give you these combination of ones and zeros, which is great. Now, if you change anything here, the output will be different. So what the reverse of this, or what Bitcoin does is, and he's going to explain this later, is that imagine if you have a combination of these ones and zeros. How will I know what do I have to run? What's the value that I'll run a SHA-256 on that will give me this combination of ones and zeros? The only way to do that will be to guess and say, okay, let me do a SHA-256 on some random numbers or some random characters to see what the output will be. And you have to guess over and over and over again. And this is the powerful thing about the proof of work concept. This is a great feature that is used in this whole ecosystem of proof of work. So this is one piece that's extremely, extremely, extremely important. So this is what miners do. When I have a subsequent video, forget about the video, watch this video. But yeah, so before I go into all that, watch the rest of this and I'll try and explain further. So let's.
For right now, our focus will just be on how such a function can prove that a particular list of transactions is associated with a large amount of computational effort. Imagine someone shows you a list of transactions, and they say, hey, I found a special number so that when you put that number at the end of this list of transactions and apply SHA-256 to the entire thing, the first 30 bits of that output are all zeros. How hard do you think it was for them to find that number? Well, for a random message, the probability that a hash happens to start with 30 successive zeros is 1 in 2 to the 30, which is about 1 in a billion. And because SHA-256 is a cryptographic hash function, the only way to find a special number like that is just guessing and checking. So this person almost certainly had to go through about 1 billion different numbers before finding this special one. And once you know that number, it's really quick to verify. You just run the hash and see that there are 30 zeros. So in other words, you can verify that they went through a large amount of work, but without having to go through that same effort yourself. This is called a proof of work. And importantly, all of this work is intrinsically tied to the list of transactions. If you change one of those transactions, even slightly, it would completely change the hash. So you'd have to go through another billion guesses to find a new proof of work, a new number that makes it so that the hash of the altered list, together with this new number, starts with 30 zeros.
So, as he said, if you run a SHA-256 on these random numbers, then you will get this series of ones and zeros. So imagine if you wanted to start with 30 zeros, you'll have to be able to figure out what number do I run a SHA-256 on to give me 30 leading zeros to start off before I get these other numbers to follow.
And because SHA-256 is a cryptographic hash function, the only way to find a special number like that is just guessing and checking. So this person almost certainly had to go through about 1 billion different numbers before finding this special one. And once you know that number, it's really quick to verify. You just run the hash and see that there are 30 zeros. So in other words, you can verify that they went through a large amount of work, but without having to go through that same effort yourself.
So once the number is guessed by whoever guesses this number, all I have to do, so let's say I figured out what the number is that will give me these outputs. So let's say I run my SHA-256. I cannot confirm that whoever guesses this actually got it, because all I have to do is run a SHA-256 on the result, and I can confirm that this is correct. So
this is called a proof of work. And importantly, all of this work is intrinsically tied to the list of transactions. If you change one of those transactions, even slightly, it would completely change the hash. So you'd have to go through another billion guesses to find a new proof of work, a new number that makes it so that the hash of the altered list, together with this new number, starts with 30 zeros.
Nice. So you have to watch that part again and again, or watch this again and again and again, but this is a very, very important piece of it. So if anything is changed, it will also change what the output of the hash will be. So just to reiterate, you do a SHA-256 on a particular number to get this output. But remember, all I have is the output. I have to guess what number or what series of numbers do I have to run a SHA-256 on to get my desired output. So you have the desired output, but I don't know what I'm going to run the SHA-256 on. So the key is to be able to, usually you run a program or you use one of those ASICs, an ASIC, to do this computation. And then once I'm able to guess, and it's not something that I can guess physically, a machine or a computer or a hardware processor, which is the ASIC does that. And it now gives me the number that will start with, in this case, 30 zeros. So, and then once that is guessed, anyone can confirm that I have the right guess by simply doing a SHA-256 on the number. I hope I explained that properly. Yeah, so that's the second piece of it. And I'll just go to the last piece, and then we'll...
So now think back to our distributed ledger situation. Everyone is there broadcasting transactions, and we want a way for them to agree on what the correct ledger is. As I said, the core idea behind the original Bitcoin paper is to have everyone trust whichever ledger has the most work put into it. The way this works is to first organize a given ledger into blocks, where each block consists of a list of transactions together with a proof of work. That is, a special number so that the hash of the whole block starts with a bunch of zeros. For the moment, let's say that it has to start with, 60 zeros, but later we'll return back to a more systematic way you might want to choose that number. In the same way that a transaction is only considered valid when it's signed by the sender, a block is only considered valid if it has a proof of work. And also, to make sure that there's a standard order to these blocks, we'll make it so that a block has to contain the hash of the previous block at its header. That way, if you were to go back and change any one of the blocks, or to swap the order of two blocks, it would change the block that comes after it, which changes that block's hash, which changes the one that comes after it, and so on. That would require redoing all of the work, finding a new special number for each of these blocks that makes their hashes start with 60 zeros. Because blocks are chained together like this, instead of calling it a ledger, it's common to call it a blockchain. As part of our updated protocol, we'll now allow anyone in the world to be a block creator. What that means is that they're going to listen for transactions being broadcast, collect them into some block, and then do a whole bunch of work to find a special number that makes the hash of that block start with 60 zeros. Then once they find it, they broadcast out the block that they found. To reward a block creator for all this work, when she puts together a block, we'll allow her to include a very special transaction at the top of it, in which she gets, say, 10 ledger dollars out of thin air. This is called the block reward, and it's an exception to our usual rules about whether or not to accept transactions. It doesn't come from anyone, so it doesn't have to be signed, and it also means that the total number of ledger dollars in our economy increases with each new block. Creating blocks is often called mining, since it requires doing a lot of work, and it introduces new bits of currency into the economy. But when you hear or read about miners, keep in mind that what they're really doing is listening for transactions, creating blocks, broadcasting those blocks, and getting rewarded with new money for doing so. From the miner's perspective, each block is kind of like a miniature lottery, where everyone is guessing numbers as fast as they can until one lucky individual finds a special number that makes the hash of the block start with many zeros, and they get the reward.
So that really is a very, 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 let me look for this important piece. So this is what mining is. Each miner goes into a pool of transactions and adds those transactions and creates a block. And then the Bitcoin protocol, what it expects each miner to do is the first miner that takes his block and is able to guess. So what the Bitcoin protocol will do is we'll say, hey, you have to guess for the first, maybe the hash has to have 30 zeros. So let's say the hash has about 30 leading zeros. You will have to now, each miner will have to guess what is the value that I have to run a SHA-256 on that will give me those leading zeros. So all these miners are all running computers which have ASIC chips, and they are very, very fast processors which are designed just for this, to be able to figure out, okay, what is the value that would give me those leading zeros. And the first miner to do that gets to be able to add his or her block onto the blockchain and is rewarded with a block reward, or what we call a mining fee. There's so much more to this, but if you can understand this concept, then everything else is I won't say easy, but this is really core of it. Now, there's more to this. Please watch the rest of the video. There are other things to consider. What happens if two miners at the same time are able to guess what the value is, and they both create or add a block to the chain? Well, then we have what we call a soft fork, and we have two chains. And so eventually, the mining community or the group of miners will listen out for which chain eventually becomes the longest chain. So you can watch the rest of that, and he explains that in detail. So this is a very good video that you should probably watch again and again. I hope I've done a good job in explaining it, but this is a very key concept of Bitcoin, and also the concept of blockchain technology came into place because of this wonderful idea of proof of work. Now, it's slow. It takes about 10 minutes each time to add a value to a block to the chain, and also there are other things to consider. This also burns a lot of electricity because you have your processor that is running 24/7 trying to guess what the value will be to solve this problem. So there are other things or other factors that make proof of work a little bit challenging, but ultimately I think it's a great consensus algorithm. Consensus means agreement, so this is a way of everybody on the network agreeing on what the property or what the state of the chain is, or the state of the ledger is. So I hope this helps. I hope this makes sense. I hope this helps. And yeah, well, I'll put a link for this video below so you can watch it over and over and over and over again. Well, that's all I have. So ladies and gentlemen, till next time, I wish for you is that you learn how to code, because coding is changing and will change the world, especially this blockchain, distributed ledger technology space. And it's my personal opinion that those who get involved early will greatly impact the future. And if that's you, let's go change the world.